Hi, this is Roger from Kankalabs, today with a video about all the errors you get in your solder station. Now, as some of you know, I'm at the moment developing new firmware for the Hekko FX951 Chinese clone or ripoff. And because I want to make this better than the original Hekko firmware, not only with more menu points, but also with a higher accuracy, I had to completely investigate all the errors that you get in a solder station concerning the temperature measurement, the control loop, etc. And it's really bothering that all the errors can be compensated without investing a cent of money, just by not ignoring the physical principles behind temperature measurement. And I promise you, all the errors that we discuss in this video are not only present in cheap solder stations, but although to a lesser degree, they are also present, for example, on our expensive JBC solder station. So, and it really annoys me. This is not rocket science, as you will see. So let's first demonstrate the two most severe things that come with all solder station. And that is, first of all, the thermal lag, which means we will see this in a second when I switch on here this ATTEN AT80D station, which I already reverse engineered and found out the errors and compensated them with different resistors, etc. in two videos, I think 1 or 2 years ago. I'll demonstrate to you. Just watch when I switch this on what temperature is displayed. I think I've set this to a set temperature of 350 degrees. And when it says that it has reached the set temperature, and what we observe here with our solder thermometer. Let's make good contact, turn it on again. I hate auto power off functions. And now let's switch the ATTEN on. And it first displays the set temperature, the 5 bars here. They say how much it is heating. And you can see it already says it's at 300 degrees, but the solder tip is at below 100 degrees Celsius. And you can see now it's already not fully heating up, just doing a little kind of PWM. And that makes the heat up time, of course, much longer than it has to be. Instead of heating full power, and you can see we're only at 300 now. And it already says it has reached the real set temperature. And that's, of course, complete nonsense. So let's see at which, so it took much longer than necessary, and there was a big discrepancy between the heat up time, between the display temperature and the true temperature at the solder tip. And now you can see we are overshooting here. So we are 30 degrees higher than the set temperature, and this is unacceptable, because when you change your solder station and go from one workplace to another, you expect that when you're used to soldering at, let's say, 350 degrees real tip temperature, that when you go to another solder station and you set it to 350, that you also get 350 at the tip and not at the display. So we're 40 degrees off here. Let's remember that, and we will later see it's no fix to program the offset temperature here of 40 degrees, or now it's already 45 degrees offset. That is not a fix, because this offset would only compensate at one exact temperature. We will just in a minute set this to 200 degrees Celsius and see if the offset is then still 45 degrees Celsius, or if the offset is then different. So, okay. We have 45 degrees offset. Unbelievable. This is, by the way, we have 2 of these stations now phased out here. So they are spare stations. One of them, I've corrected the wrong gain of one of the op amps. And this is the original one, without the modification, without the fix. So let's set this down to 200 degrees Celsius. And I'll spare you the waiting time until the tip has cooled down. But again, now it says it has cooled down to 200 now. And what do we have at the tip? 347. Unbelievable. So 150 degrees discrepancy between the display temperature apparently at the place where the heat sensor is placed inside the iron, and the true temperature is still falling very slowly. So in fact, we have a set temperature now of 200 degrees, but the tip temperature is, even if it falls down a bit, because it's still heating again. So it says it's inside the control loop is 85 degrees off now. 2 minutes ago we had 45 degrees offset at 350 degrees set temperature. Now we have 80 degrees offset at 200 degrees set temperature. So there's no use in trying to program an offset into this stations, which you can do, but the offset function has a totally different purpose. It's just to compensate for different tips and not to compensate for the errors they made in the electronics, or better in the mathematics behind the electronics. So we have a slope error and an offset error. Unbelievable. And all these goes down to the thermal properties of the heater, the ceramic around the heater, the contact between the ceramic heater and the solder tip, and all the thermal properties. So what we'll do is we'll discuss every single error and then make a simulation, and I've already prepared that, and I can promise you we can reproduce all the errors that we saw here with an electrical simulation in LT-SPICE, so that we know that the theory that we develop, where the errors come from, is verified by an electrical simulation of the thermal properties and of the thermal behavior. And that is also the solution how we can solve this problem, how we can fix this, partly in hardware, by laying out the hardware the right way, partly in the firmware, in the software, in the layout of the control loop, and how measured temperature is translated to real tip temperature. This is possible, but apparently nearly nobody does this. I found out, I've downloaded a few manuals of the more expensive hacker stations because I wanted to know what do they implement in the firmware in the more expensive hacker stations. And there I could find at least one station where they knew about these problems and where they have a second compensation factor that you can program in software. But let's do it step by step and start with a summary of what problems and what error sources we have. So let's first of all make a little graph about the relation between the displayed temperature, or in other words, what the solder station thinks that the temperature at the solder tip is, and what really is the true temperature measured at the solder tip with an extraneous solder tip thermometer. Now the software thinks that the relation is this way, that it's perfectly linear and starts at 0. To be exact, because we only deal with thermocouples, it starts at 0 degrees above ambient. And so what most solder stations do in software, they take the thermovoltage. I will talk a little bit, 2 or 3 words about thermocouples used to measure, times the gain of the op-amp times a factor, and that is basically what comes into the ADC. And the factor is just to convert analog digital units to the true temperature, or to the display temperature that you get in your display. But we have seen, first of all, there's the thermal lag. We will discuss this in a few minutes. But when the control loop and the temperature has stabilized, you could get The true behavior could be this way. First it starts with a constant offset. Then we have a different slope, and then it might be that even there is not a perfectly linear relation between the thermal voltage and the temperature, but at some points or over the whole range it's slightly nonlinear. So already here we have first an offset error, second a slope error, and third a linearity error. Shift this up a little bit. So the offset could come, for example, from, if you're using non-precision op-amps, it could be just an offset from the op-amp, because thermocouples give only microvolts per degree Celsius or per Kelvin, and that means, for example, a standard op-amp with 1 millivolt gives you already 20, 30 or 40 degrees offset. It could also be what I've explained in another video, the so-called cold junction compensation, because a thermocouple can only measure the temperature relative to ambient. And if ambient temperature inside the solder station is not measured with an extra sensor, this could produce you, of course, an extra offset. The slope error is due. It could be also a different gain setting of your op-amps, but we will later see that the slope error in most cases has a different cause, simply because the engineers did not take into account that the slope at the solder tip is different than the slope of the temperature curve at the point where the thermocouple is sitting. This will all become clear in a few minutes. And the linearity error, well, we will not discuss here the other method of measuring the temperature inside solder irons, and that is with thermistors. We'll only deal with thermocouples integrated into the heater or near the solder tip, etc. And usually you assume that you have a so-called type K thermocouple, which is quite linear. We will later see, I've made a graph how the deviation from linearity between 200 degrees Celsius and 450, how large the non-linearity becomes. It is negligible with type K ones, but I've discovered, I believe, that the Hecko T12 and T15, the modern solder tips, are type N ones, and they have a much bigger non-linearity. And so this could be just due to the thermocouple inherent physical non-linearity. If you don't take this into account, you get this kind of slope error, that in fact your curve is not perfectly linear, but it slopes up or down over a certain range. So, and now you see why it makes no sense to program an offset. You have only the true temperature is only at one point matches the displayed temperature. Now if you program a software offset, you just shift one curve up or down, and you just only shift the point where this one point where the two curves match, but that is not the way how you should do it. What you want to have is that your display temperature becomes plus or minus, let's say 2 degrees Celsius or 4 degrees Fahrenheit, matches just the true temperature. And this is really possible, and this is not rocket science. This is basic engineering knowledge that every engineering student will have learned after the first semester in practical electronics. So I don't know why nearly not a single station I've seen just takes all the factors into account. But now let's take a look at the thermal properties. So let's sum it up until now. We have, how could we compensate for this? For these first three ones here. The offset, when it's due to the op-amp, you just take a precision op-amp, or you subtract, which is not the best way to do it. You subtract the offset of your non-precision op-amp. The easiest way is just take a precision op-amp for less than $1 or euro. The cold junction compensation, I will do it in the Hacker Station just by measuring the internal temperature of the microcontroller. Is a relatively good approximation of the temperature inside the solder station. It's not the perfect way how you would do it. Normally you would place a second thermal sensor directly at the places where the thermocouple leads are soldered to the PCB. But the second best approximation is measuring the temperature in the microcontroller, and this will give you probably only a 2 or 3 degrees Celsius error, which is much better than assuming just a fixed value of 23 degrees Celsius, for example, as is most often in your lab, but not always. The slope error can be taken either in hardware by changing the gain of the op-amp, or still better, in software into account. And we will later see that the slope depends on the used solder tips. So small solder tips have a different gain or a different slope than large solder tips. And in most manuals you can read, well, the software programmable offset is in fact for that purpose, for using different tips, but that's completely wrong. You have to change the slope and not the offset. The offset shifts the wrong curve up and down, but in fact you have to adjust the slope of your internal approximation of your measured temperature value and the true temperature. And so it would be much better not to have a programmable offset, but a programmable gain for different tips that you use, and additionally perhaps a second menu entry for setting a fixed offset additionally. And the linearity error, well, nothing is as simple as that. Either use a type K, or if you have to rely on what you get when you buy the tips with the integrated heater and sensor, yeah, you just can make a polynomial approximation. If you know it's a type N, there are published values for how the true curve is running, and you can approximate this with a 1, 2 or 3 degree polynomial. Nothing easier than that to do in software, and you can in software null out this nonlinearity. So that's as simple as that. But these were the easy things to understand and to compensate. And I believe the next part, which is the most important in this video, that 90% or 99% of all the engineers who design solder station, they even don't care about this topic, or they don't understand it. So let's come to the thermal properties of solder irons, heaters, solder tips, and how it all works together. So let's start with a short introduction into the equivalence between electrical and thermal calculations or simulations. Of course, you can skip this part if you know everything about thermal calculations. And that is also the reason, because of this equivalency, that we can later simulate the thermal behavior and all the errors we saw with LT-SPICE. Now, first of all, we have, of course, a source of something. In thermal, of course, this is the power, in our case, that the heater produces, and the unit is watts, or what is nothing else than joules per second. And the electrical equivalent is not a voltage source, but a current source. So This is the European symbol for a current source. So the equivalent of a thermal power source, in other words a heater, is a current source with the unit amps, and amps is nothing else than coulomb per second. There's a reason why I write different definitions of the units here, because we will later use that. So here we have our current, and we will later see we only need Ohm's law and how a capacitor charges to do all the simulations and all the calculations. So what else do we have in Ohm's law? We have our resistance. And of course in electrical, that is our resistance R in ohms or volts per amp. And in thermal calculations, that is the thermal resistance. And I'm pretty sure you already have heard this in conjunction with heat sinks, etc. And the unit here is kelvins per watt power. So the third thing in Ohm's law is voltage. And voltage in electrical calculations is always the voltage relative to ground. So there's nothing like an absolute voltage. So the right thing to note is delta U relative to ground. Usually you only find U because it is assumed that you refer your voltage measurements to ground, but we will see in a second that this is quite important, relative to ground. In other countries they are using the letter V, the capital V, but you will most often see me using a U for not to mix it up with the unit of volts here. So the unit is of course volts. And now comes the interesting thing. In thermal calculations, the equivalent to our voltage is the temperature T, or better delta T, measured in Kelvin or degrees Celsius. As you might know, Kelvins and degrees Celsius have the same slope. The only difference is the 0 point. But when we're subtracting two temperatures, it doesn't matter if we subtract them in Kelvin or subtract them in degrees Celsius, because the offset of Celsius just cancels out or subtracts itself out. So one viewer once commented why I was using degrees Celsius here, or here even in the thermal resistance. It doesn't matter because we are only talking about temperature differentials. And so we have to have something like the 0 point, let's call this the ground. In electrical calculations, of course, the voltage is related to ground if we are talking of kind of absolute voltages. But remember, there's nothing like a true 0 point. It's always an arbitrary reference inside your circuit that you design as ground. Even Earth is not absolute 0, because you don't know if the Earth, the planet Earth, is not charged up by the solar wind and the Van Allen belts and whatever to perhaps even several million volts. So this is always a relative ground, usually in your circuit. One point or one bus will be called ground. And in thermal calculations, that is the ambient temperature of your environment. So, and there's one thing left, and that is a capacitor, or the capacity. Well, with its circuit symbol. Now in electrical, this is clear. This is the capacitance C measured in coulomb per volt, or a coulomb is also an amp second per volt. We will later need this just to interpret our LT-SPICE results in the right units. When LT-SPICE, for example, displays a voltage, we know, aha, it's not the voltage, it's the temperature differential relative to ambient. And you might have heard also something, an expression like a thermal mass or thermal capacity, and that is measured in joules per Kelvin. So how many joules do you need to heat up, for example, your solder tip for 1 Kelvin? Or another expression would be watt seconds per Kelvin. So you just have to remember these equivalencies, and if you know how to deal with combinations of a current source, a resistance, a capacity and the voltage, then you are simply able to do any thermal calculation. So this is the basic equivalency, and now we'll look upon how a solder ion behaves thermally and then translate this to the electrical equivalent and can then simulate this. And that is including, which we will see, the thermal lag between our temperature of our sensor, of our thermocouple, and the temperature at the solder tip. So when we take apart one of these standard so-called indirect heated solder ions, we see three things. First, this is the ceramic heater, but it's not the ceramic that is heating. Inside it is probably simply a nichrome wire or something like that hidden, and that heats this ceramic cylinder here from the inside. And then comes the connection between, now the solder tip comes here, slid over the ceramic heater, as you can see, with only making point contact, and then there's still some distance to the solder tip itself, and this is all covered or screwed together with this metal thing here, however this is called. And you can already see when I screw this together, if I get it screwed together again, if I find the thread. Here, look, in these cheap ions, that you can move the solder tip while it is firmly screwed down. This also is an indication of a bad thermal contact, and that is one of the reasons why these indirect heated solder ions give much greater error, take much more time to heat up than the modern directly heated solder tips that we will take a look at later. So, but let's go back to the heater and start with that. So the heater is not what you see here, this white ceramic. It is inside the ceramic, and it is with 99% certainty this will be simply a wire heating up by the current flowing through it, and integrated in the wire is the thermocouple. So we'll take a look at this in a drawing. So let's suppose this is our heater element, and at the tip or at the front end of it is sitting our thermocouple. Now, which thermal properties do we have to deal with this? Well, our heater wire certainly has a thermal mass, but which gets the symbol C because it's basically a capacitance. So this is not the electrical capacity, it's the thermal capacity equivalent to an electrical capacitance, but the electrical capacitance doesn't come into play. then of course the heater wire will give off its heat to ambient, because we leave out first of all the ceramic and everything around it. Let's see it that we have the bare heater wire only surrounded by air, and we have a thermal resistance RTH for thermal from heater to ambient. And what else do we have? Of course we put some power into it, but electrically we do this with a current source. So one thing is still missing, and that is our power source. Now in thermal calculations we know we have our power P, but in electrical calculations this is in fact a current source. So to clarify this a little bit again, the differences. And when we have a power of, let's say, 60 watts, for example, we're using in the electrical simulation a current source of 60 amps. And if we have, for example, a thermal capacity of 0.25 or something like that joules per Kelvin, we're using in our electrical simulation just 0.25 farad. And if we have, for example, a thermal resistance from heater to ambient of, let's say, arbitrarily 20 kelvins per watt, our electrical resistance is just in the base units 20 ohms. And if you want to know the temperature at one point, and in this case it's here where the thermocouple sits, that gives the temperature differential to ambient in Kelvin or degrees Celsius, doesn't matter. And in our electrical simulation we just probe our voltage in volts. And the amount of volts, the number, is exactly identical then to the temperature in Kelvin. So you see how easy it is. You only know how to transform the different parts of your thermal chain here, and then you can probe, for example, how your temperature is running by probing the voltage. So let's go with this model into LTSpice. Okay, first of all we leave out the thermal resistance to ground, but only take a look at what happens if we just charge our capacitor or our thermal mass with a constant current, aka a constant power, into the thermal mass. So let's go into the simulation, and first of all let's take a look at the current. And you see, as I told you, it starts at 20 amps, aka 20 watts of power, thermally speaking, and then drops after 60 seconds down to 5 amps, aka 5 watts. And now we take a look at the temperature at our bare heater element, and you can see it rises linearly, just as we expect if we charge a capacitor with a constant current. Of course, to unreasonable high values here, nearly 5 kilovolts, aka kilokelvins, after 60 seconds, and then with the lower current or lower wattage into the capacitor, it rises with a smaller slope, but it would still rise up to infinity if the current or the power would go on forever, because there's one thing missing, and that is our thermal resistance to ground. So let's add this, and we'll give it a value of 20 ohms, aka 20 kelvins per watt. and see what it looks now. Aha! So that looks like something that has more to do with reality. The temperature, the blue curve here, now rises up to, you can read 400 volts, but in fact this translates to 400 kelvins above ambient with the high current. And then when we lower the current, of course, it settles to a lower voltage, aka lower temperature in the range of 100 kelvins above ambient. So the first part of our simulation already matches reality. Now let's take this a step further. Okay, the next thing we have to take into account is that our heater wire is not sitting in the air, but it is completely encapsulated by this ceramic cylinder. And let's draw this, how it looks schematically in reality. We have our ceramic cylinder. Inside it is our heater wire with the thermocouple, and it gets its power from our current source or power source. But now we don't have a thermal resistance to ambient, but now all the power from our heater goes via the thermal resistance from heater to ceramic to the ceramic cylinder, and so this ceramic cylinder itself of course has a thermal mass, and from there, if we don't cover it with anything, if it is sitting now in bare air or ambient, then we have a thermal resistance from the ceramic to ambient. So our equivalent circuit would look like this. We have our current source, the thermal mass of our heater, then a thermal resistor to the ceramic, and that itself has its own thermal mass, and from there it goes to ambient with another thermal resistor. And what's of interest is what is the temperature now here at the heater, and what is the temperature here at the outside of our ceramic cylinder. And for that we'll go with this circuit again into LTSpice.